Hello everyone, welcome again in Eng-Man YouTube channel. So we will continue our learning on PVTP software, still about compositional oil modeling. And in previous video, we have done the calculation for the regression. And in this video, we will deal with the primary quality check. Until this video, we will continue with the validation and then second regression. And yeah, let's see what will happen later. Okay, so now once the regression is complete or the error is within our tolerance, the iterations have been exceeded or no further improvement can be made, the regression error details and output fluid will be active. Yeah, regression error details as well as the output fluid. And you can also check the resulting fluid in, I called it fluid regression 1. And for the statistics, you can see the regression statistics, iteration number 200 with very good error. Here, the best error as well as the error. Okay, so that's the thing. And let's check the regression error details. I'm gonna expand this, okay? So we have the first column is the stream, PVT fluid. And then for the calculation, PSAT, separator, and then differential liberation. And then for the variable, we have saturation pressure from PSAT, liberated gas oil ratio from separator, oil density from the separator, and oil density from deflip. And this is the unit, and then the target value, actual value, and the error percent. You can review it. You can see the error in percent is very small, very, very small. So I think it's quite satisfactory. Okay, the liquid density above and below the bubble point or the saturation pressure. Let's see the oil density. Yeah, okay. As well as for the GOR. Yeah, okay, the value. So the saturation pressure and GOR and the liquid density above and below point have all been matched to a high degree of accuracy, as can be seen by the errors. Yeah. Okay. From this, it can be concluded that we appear to have met all of our primary regression objectives, which are to have good match for the liquid density, all right, above and below the saturation pressure, and then the saturation pressure itself, and the GOR. Next, it is important to verify that the calculated critical properties, or TC and PC, follow smooth physical trends, the natural trend. If there are discontinuities such as a step change, significant change, this can be a sign of the regression overcompensating for another variable or the variable not having a large effect on the regressed property. This can be investigated by plotting the critical temperature and critical pressure as a function of the component number. And that's the thing that we will do. To do this, we go to output fluid, still under this regression. And let's see, we have component name, composition, TC, PC, eccentric factor, omega A, omega B, critical volume, and so on and so forth for the properties. This is the more properties if you are interested. Binary interaction coefficient. And the thing that's very important now to check is the plot. Okay, from here we can plot the critical pressure and critical temperature against the component number. Okay, so on the horizontal axis we have component number. Now for the vertical axis, let's plot TC first, critical temperature, and critical pressure. Or you can select for the left y-axis critical temperature and for the right y-axis the critical pressure. Beautiful. Okay, we can expand this. Okay. And let's see, the blue line is the critical temperature, the regression. And then here, the orange line is the critical pressure versus component number, the regression. So for the blue and the orange lines are, for the regression. And then for the critical, sorry. So let me do this one step at a time instead. Okay, so let's start with critical temperature. So we have the blue line first, critical temperature versus component, yeah. And then this is after the regression. So this is resulting from or after this regression. And before the regression, the result is shown by the orange line. Okay, let's start with that. So you can see after the regression, we still can achieve very good match. Okay, and the trend looks, natural. There is no significant or step change. Okay, from this plot, once again, it can be seen that the critical temperature has not changed significantly and appears to follow a physical trend. Okay, and then let's continue with the critical pressure. Okay, you see, or maybe I can check the critical temperature first. Okay, now we have this one, the blue line. I don't know what color it is, but this is for the PVT fluid and the orange line for the regression, so after regression. And still we can say that the critical pressure have been slightly reduced, and if anything now follow an even more natural profile. Okay, once again, the orange line is for the regressed fluid or the fluid after regression. Okay, to conclude, we achieve very good and natural result after the regression. If the critical properties and or phase envelope are found to be unphysical, or the surface properties change significantly, then the regression strategy requires a review or requires a redo instead. As part of this review, it should be established whether the pre-regression model provides a good enough description of the fluid behavior, as the regression is only intended for fine-tuning. If it is not the case, then the pseudo-properties, the pseudo-profile and splitting, as well as the binary interaction coefficients could be reviewed, need to be reviewed. Alternatively, the property causing the behavior, the unphysical phase envelope due to large BICs, could be even omitted from the regression, or the regression could be repeated using only the heaviest components. Okay, so still a little bit note about the strategy to improve the matching. Okay, but at least for now, we have achieved natural look for the critical properties, the critical pressure and critical temperature. So we can say so far we have done very good job. I'm gonna close it here, and on the next video, we will do the validation for the regressed fluid. Until then, see you again, and thank you so much.